All right, let's dive in. We're going to take a journey from the totally invisible world of atomic forces all the way up to the massive structures that define our modern world. And the bridge that connects those two? Well, it's a single, incredibly powerful concept: elasticity. I mean, have you ever really thought about it? Why does a rubber band snap back? How can a massive bridge flex under traffic but not just crumble? The answer to all of these questions comes down to this one fundamental property, this hidden strength inside materials called elasticity. Now, to really get this, we have to look at things on two totally different scales. If you zoom way, way in, down to the microscale, a material is what we call anisotropic. Basically, that means its properties change depending on which direction you're looking, kind of like the grain in a piece of wood. It's just a jumble of crystals all pointing in different directions. But when you zoom out to the macro scale, the world where engineers actually build stuff, all those random directions just average out. The material becomes isotropic, predictable, uniform, and reliable no matter which way you pull on it. So here's the bottom line, the thing that's absolutely crucial. Engineers rely on this property to keep us safe. See, for every material, there's a safe zone. You can stretch it, you can bend it, and it will pop right back to its original shape. No harm done. That right there is the golden rule of engineering. You design everything, and I mean everything, to live its entire life inside that elastic zone. It ensures things can bend, but they will never ever break. Okay, but why? Where does this incredible bounciness actually come from? To find the real source, we have to peel back the layers and go even smaller, way smaller than those crystal grains. The secret, it turns out, is at the atomic level. I want you to imagine that every single pair of atoms is connected by a tiny invisible spring. Now, these atoms have a perfect distance they like to be from each other. They're low-energy happy place. If you try to pull them apart, those springs pull them right back together. If you try to squish them closer, the springs push them apart. Elasticity, at its very core, is nothing more than the combined effort of trillions and trillions of these atomic springs, all resisting being moved. Okay, so we have this beautiful picture of atomic springs. But how do we turn that into actual math that an engineer can use to build a bridge? Well, you start simple. You start by just stretching something in one single direction. And in just one dimension, the whole behavior boils down to two simple but incredibly powerful rules. The first one is Hooke's law. That equation up top basically says the more you pull on something, that's the strain, the harder it pulls back. That's the stress. It's a direct relationship. The second rule is something called Poisson's ratio. And you've seen this a million times. Stretch a rubber band. What happens? It gets thinner in the middle. This ratio just measures exactly how much thinner it gets. That letter E in Hooke's law, that's the magic number. It's called Young's modulus, and it's a direct measure of a material's stiffness, basically how strong those atomic springs are. And wow, just look at the difference here. Aluminum is pretty stiff, but steel is almost 3 times stiffer. And then there's tungsten, which just blows them both out of the water. More stiffness is just more atomic resistance. Simple as that. But here's where it gets really interesting. Look at that other value, V, Poisson's ratio. While the stiffness is all over the map, from aluminum to tungsten, that get thinner when you stretch it property is surprisingly consistent. For most metals, it hangs out in this tiny little range. And that's a huge clue that some of these behaviors are way more fundamental than others. So we've got the rules for 1D down. But let's be real, the world we live in isn't a 1D line. Things get pulled and pushed from all sides. So how do we build up from this simple starting point to the complex 3D world we actually live in? Well, the secret weapon for handling all that complexity is a beautiful idea called the superposition principle. It's brilliant. It basically says, don't panic. Take the complicated problem and just break it down into a bunch of simple problems you already know how to solve. We can analyze the pull in the X direction, then analyze the pull in the Y direction, and then just add the results together. And this is what that looks like in math. The total stretch in, say, the X direction is actually a competition. It's a tug-of-war. You have the direct pull on that axis making it longer, but at the same time, the pull on the y-axis is causing that Poisson effect. It's squeezing the material from the sides, trying to make it just a little bit shorter. And once you get that logic for 2D, going to 3D is a piece of cake. You just apply the same pattern again. The stretch on any given axis is always the direct pull on that axis, minus the squeezing effects from the other two. And boom, that's it. This is the complete playbook. These 3 equations describe how any isotropic material stretches in our 3D world. Now, I know we've thrown a few different constants at you. E for stiffness, V for that squeezing effect, G for shear. It can seem like a lot, but what if I told you they are all secretly related? That there's a kind of beautiful, simple connection between them, like a Rosetta Stone for materials. This is the grand realization, the big aha moment. Even though we've defined all these different ways to measure how a material responds, you only need to know any 2 of them. Pick any 2. Stiffness and Poisson's ratio are the easiest to measure, and from those 2, you can mathematically derive all the others. The entire mathematical architecture for that material is suddenly unlocked. So let's just recap the journey we took. It's pretty amazing when you think about it. We started down at the very bottom with the push and pull of atomic bonds. We saw how that gives rise to a material's core properties. We then translated that into simple 1D mechanics, used the clever trick of superposition to build it up to 2D, and then finally, we arrived at the complete equations that govern our 3D reality. You see, this is so much more than just a set of equations. It's the mathematical translation of trillions of atomic springs all working together in unison. It is the invisible architecture holding our entire world together, a hidden blueprint for creation. And now that you can see it, now that you understand the rules, the only question left is, what will you build?